Have you ever pondered the mysteries of the universe, like what would happen if you fell into a black hole? The question itself teases our curiosity, doesn't it? It's a question that has intrigued scientists, researchers, and even those who simply gaze at the stars for decades. Black holes, one of the universe's most mystifying phenomena, are regions in space where gravity pulls so much that even light cannot escape its grasp. They're like cosmic vacuums, sucking in everything that comes too close. But they are not just space oddities, they are also key players in the grand cosmic drama that unfolds across the universe. Imagine an object so dense, so heavy, that its gravity distorts space and time around it. Picture this object having a gravitational pull so strong that once crossed, nothing escapes its clutches. Not a planet, not a star, not even a beam of light. That, dear listeners, is a black hole. Yet despite their ominous name and reputation, black holes aren't just cosmic monsters lurking in the shadows. They're fascinating objects that challenge our understanding of physics. Black holes force us to question, to explore, to push the boundaries of what we believe is possible. To truly understand a black hole, we must venture into the realms of quantum mechanics, Einstein's theory of relativity, and high-level physics. We're not just delving into astronomy here, we're diving into the very fabric of the cosmos. So, what's inside a black hole? What happens when you get sucked into one? And how do black holes influence the universe around them? These are just a few of the tantalizing questions we'll be exploring. Prepare to have your mind expanded and your understanding of the universe deepened. We're about to embark on a journey into the heart of one of the most enigmatic phenomena in the cosmos. So buckle up as we delve deep into the enigma that is a black hole. Black holes are not just fascinating, they are born from the remnants of massive stars. But how does this transformation occur? Let's begin with the life of a star. A star is an astronomical object composed of mostly hydrogen and helium in a state of plasma, with its core undergoing nuclear fusion. This fusion process produces light and heat, which is why stars shine. However, this can't go on forever. At some point, the star exhausts its nuclear fuel. When a massive star, much larger than our Sun, depletes its nuclear fuel, it can't sustain the heat and pressure to counterbalance the force of gravity pulling everything inward. This leads to the star collapsing under its own gravitational pull. The outer layers explode in a supernova while the core continues to collapse. Now here's the mind-bending part. The core collapse doesn't stop. It keeps going until it forms what we call a singularity, a point in space with infinite density. In simpler terms, imagine squeezing the entire Earth into a tiny point, so small that it's almost non-existent, yet still holding the same mass. That's a rough idea of a singularity. This singularity is wrapped in a boundary called the event horizon, which is the point of no return. Anything, including light, that gets too close and crosses this boundary will be sucked in and can't escape. Hence, we get a black hole, an object with extreme gravity that nothing can escape from. But don't mistake a black hole for an empty void. It's a huge amount of matter packed into a very small area, creating a gravitational field so strong that not even light can escape its pull. So, in essence, a black hole is a star that has died and collapsed under its own gravity to a point of infinite density, where the known laws of physics cease to apply. So, from the remains of a dying star, a black hole, a region of infinite density, is born. Now, you might ask, what does Einstein's theory of relativity have to do with black holes? Well, sit tight, because we're about to dive into the fascinating world of theoretical physics, where space, time, and gravity intertwine. Einstein's theory of relativity, which is actually two separate theories, special relativity and general relativity, fundamentally changed our understanding of the universe. Special relativity, published in 1905, introduced us to the concept that space and time are intertwined into a four-dimensional fabric known as space-time. It also proposed that the speed of light is the same for all observers, no matter their state of motion or of the source of light. A decade later, Einstein presented the world with his general theory of relativity, which is the one we're focusing on. This theory proposed a revolutionary idea. Gravity is not a force transmitted through space, as Sir Isaac Newton had proposed, but a warping of space-time itself by mass and energy. So, where do black holes come into play? Let's imagine the universe as a trampoline and a heavy object placed in the center as a star. The star warps the trampoline, creating a dip. The heavier the star, the deeper the dip. Now imagine if the star was so heavy and dense that it caused the trampoline to tear, creating a hole. That, my friends, is a simplistic way of visualizing a black hole. In the context of space-time, a black hole is a region where the warping is so intense that nothing, not even light, can escape its gravitational pull. This concept directly stems from Einstein's general relativity. The theory predicts that when a massive star exhausts its nuclear fuel, it will collapse under its own gravity to a single point in space, known as a singularity, surrounded by an event horizon from which nothing can escape. Einstein's equations thus predict the existence of black holes, these fascinating cosmic objects we are discussing. So next time you gaze at the night sky, remember the intricate dance of space, time, and gravity that shapes our universe. Ever heard of the term spaghettification? Well, it's as fascinating as it sounds. Let's dive right in. To understand spaghettification, we first need to comprehend the concept of the event horizon. Picture this. The event horizon is like the point of no return for a black hole. It's an imaginary boundary around a black hole from which nothing, not even light, can escape. Once you cross this threshold, you're inexorably drawn towards the black hole's singularity, its center of infinite density. But what happens as you near this point? This is where the theory of spaghettification comes into play, and it's not as delicious as it sounds. It's a term coined by the renowned physicist Stephen Hawking, and it describes how an object falling into a black hole would be stretched and distorted by the immense gravitational forces. Imagine you're an astronaut, feet first into the black hole. The gravitational pull on your feet would be stronger than that on your head. This difference, known as the tidal force, would stretch you out, making you look like a long piece of spaghetti, hence the term spaghettification. But it doesn't stop there. As you continue to fall, these forces would also compress you horizontally, thinning you out. You'd essentially become a stream of atoms spiraling into the singularity. It's a violent end, but don't worry. You'd be long gone before the stretching began, thanks to the intense radiation and high-energy particles near the event horizon. In essence, the event horizon is the ultimate boundary of a black hole, and spaghettification is the extreme result of its immense gravitational pull. It's a testament to the incredible and sometimes terrifying physics that govern our universe. So, if you ever decide to visit a black hole, remember to avoid spaghettification at the event horizon. Black holes are not just destructive forces, they play a crucial role in our universe. Despite their reputation as cosmic vacuum cleaners, gobbling up everything in their path, black holes are not merely agents of destruction. On the contrary, they serve as vital components in the grand machinery of the cosmos, playing pivotal roles in the formation and evolution of galaxies. Imagine black holes as anchors around which the stars within a galaxy revolve. Without this gravitational linchpin, the stars would simply scatter, leaving behind a barren void instead of the majestic spirals we associate with galaxies. Black holes, especially the supermassive ones at the heart of galaxies, exert a gravitational pull so strong that they hold these star systems together. Furthermore, black holes contribute significantly to the life cycle of stars. When a star ends its life in a supernova explosion, it can leave behind a black hole. This black hole, in turn, can trigger the birth of new stars by compressing the surrounding gas and dust. This cycle of stellar death and rebirth, mediated by black holes, is a fundamental process in the universe. But the influence of black holes extends beyond their immediate neighborhoods. Through phenomena known as jets, black holes can channel matter and energy back into the universe. These jets, shooting out from the poles of the black hole, can travel across vast distances, enriching the intergalactic medium and potentially influencing the formation of galaxies in far-off regions. Moreover, black holes are key to our understanding of the fundamental laws of physics.
They challenge our comprehension of reality, pushing the boundaries of what we know about space and time. From the singularity at their center to the event horizon that marks their boundary, black holes provide a unique testing ground for theories of quantum gravity, potentially bridging the gap between quantum mechanics and general relativity. Indeed, black holes, the stellar monsters, are fundamental to our understanding of the universe.
Today, we've unraveled the mysteries of black holes, from their birth to their role in the cosmos. We've journeyed from their formation, a cosmic event of unimaginable power, to the enigmatic event horizon and the phenomenon of spaghettification. We've delved into Einstein's theory of relativity, a cornerstone in understanding these celestial phenomena. And we've seen how black holes, far from being mere cosmic curiosities, play a crucial role in the universe's grand tapestry. As we continue to explore the cosmos, who knows what other mysteries black holes will reveal to us?